Gauri sir. Hello. Pushpa madam.
Again, sir. Sir, good afternoon.
हाँ ठीक ठीक सर ठीक
हाँ good afternoon.
Good afternoon sir. Okay. So now experiment will start today. First experiment.
हाँ first experiment will be
Okay.
started today.
Okay. ठीक okay.
Just waiting for 1 or 2 minutes
Okay.
so that maximum student.
Okay. Right. तो 61 student already present. 61. Okay.
Exactly at 4:10 we will start, sir.
Okay, no problem. Okay. ठीक.
Very good evening to all of you present here. Today we will be starting with our first experiment of microwave and antenna laboratory, that is quarter wave transformer design. Okay. Yesterday I had already sent you the manual of the experiment. You might have gone through the manual, I believe. So we will start. I hope that everyone has installed the CST Studio Suite in their laptop. I will demonstrate today the CST environment after demonstrating the brief theory part of the first experiment. Okay. First of all, let us. I hope the screen is visible, right? Please somebody respond.
Yes, sir.
Yes, sir. Okay, this very manual I had sent yesterday night. The experiment titled Design of Quarter Wave Transformer for Impedance Matching in Microwave Transmission Lines. By this time, every one of us know what is a quarter wave transformer, because it has been already taught in the previous semester in your electromagnetic waves and antennas. Just to revisit what is quarter wave transformer, first of all, let us know what is the requirement of quarter wave transformer. For any transmission through a network, we require that maximum power is delivered to the load. For that, maximum power transfer theorem is invoked, and it requires that input impedance must equal the load impedance. Okay. But what if the load impedance is not equal to the input impedance? Obviously, the maximum power will not be transferred to the load, and thereby most of the power will get reflected after it is incident in the load, right? So we go for a design that is a quarter wave transformer to match the transmission line. Suppose we cannot always change the load. This is the desirable load, ZL. That ZL need to be matched with the help of a quarter wave transformer. So what is the function of that quarter wave transformer? See, lambda by 4 section of a different transmission line. See, Z0 is the characteristic impedance of the original transmission line to which the load was connected initially, and the load is removed and is connected to the original transmission line through a lambda by 4 section of different transmission line. Now, how do we choose this lambda by 4 section? Okay, lambda by 4 section is chosen corresponding to a particular frequency. Lambda corresponding to a particular frequency. Suppose if you want to design this network for a 4 gigahertz transmission, fine. So lambda by 4 is according to that. Now, you cannot choose any transmission line. You have to choose a particular transmission line, Z0 dashed. Now, the choice of this transmission line is such that this Z0 dashed must be equal to under root Z0 into ZL. What is this Z0? Z0 is the characteristic impedance of the original transmission line, and ZL is the load impedance. So, what we have done in short, for matching this transmission line, we require to disconnect the load first of all. We have to reconnect this load through a lambda by 4 section of a different transmission line of characteristic impedance Z0 dashed, where this Z0 dashed is equal to under root Z0 into ZL. Right. Now we will have a very interesting physical feel that how impedance matching does not take place. So in the previous class, I devoted much of the time in explaining that how the S parameter will look like, right? When you have a very good matching. So we will have the S parameter curve, S parameter dB curve that lies below minus 10 dB. Fine. So if it lies below minus 10 dB, definitely we will understand that yes, we have achieved the process of matching the transmission line. Okay. So for understanding this quarter wave transformer, let me take a problem. That problem is design a quarter wave transformer to match a 50 ohm microstrip transmission line. See, we will understand this very concept by using a microstrip line structure. Design a quarter wave transformer to match a 50 ohm microstrip line with a load impedance of 150 ohm. Try to understand. What is the meaning of this? Design a quarter wave transformer to match a 50 ohm transmission line. See, the original transmission line has characteristic impedance 150 ohm. This 50 ohm microstrip line itself means that 50 ohm is the characteristic impedance of the original transmission line to which a load is connected, and that load is 150 ohms. Fine. And the diagram looks like this. A microstrip structure has 3 layers, one being the ground with a dielectric, and then a strip line. Okay. This strip line is placed in this particular fashion as shown in the figure. Right. This particular strip line has characteristic impedance 50 ohms. Now, how do we choose or how do we understand that 50 ohm is the width of this particular? I mean, what is the width of this particular strip line if it has at all the characteristic impedance of 50 ohms? Fine. So this characteristic impedance 50 ohm has width W. Say for example, if you want a transmission line to have a characteristic impedance 75 ohms, definitely your width will change and that width will reduce. If you want to design a strip line whose characteristic impedance is 120 ohm, the width of this line will again decrease. So what I want to say is that if you increase the impedance, characteristic impedance, the width will decrease. Fine. Now, how do we find the width of the transmission line? Actually, there is a process called analysis and, I mean, what we say, analysis and synthesis of transmission lines. You can refer to any standard textbook. There you will find that analysis and synthesis of transmission lines. A very empirical formula is given, a very big empirical formula is given. That particular formula will give you the relation between width of the line and the impedance. Okay. And also different other parameters like height of the substrate, what is the dielectric constant of the substrate. All these things are generally given. That I leave it as an exercise for you. Okay, so it requires a very tedious calculation. There are various open software available in the internet where that analysis and synthesis of transmission lines can be done very easily. That particular software has in-house code of that particular formulas which are given in any standard textbook, like Principles of Electromagnetics by MNO Sadipur, the textbook that was provided to you in the previous semester, or Microwave Engineering by DM Pozar, any standard textbook available, you can find it out. Okay. You can take it as an exercise. How do we find that? I will show you a very interesting process rather than going for the direct calculation. That process is actually how do we use the software called AppCAD. Now, please somebody respond whether you can visualize the screen.
Yes, sir.
Yes, sir, it is visible.
Okay.
Yes.
Okay, so you can search in Google AppCAD. You have to search in this way, AAPPCAD. The uppercase and lowercase should be typed in the fashion as shown in this particular window. Otherwise, you will get different other links. Okay, and a very small exe file will be found. You can get it downloaded and start the application. It will take a very small memory. Okay. Now we are designing transmission lines. So in the left bottom corner, you will find different areas to work with. So here you will find transmission lines. So let us click in this transmission lines, right? So if you click in this transmission lines, you will find various forms of transmission line available over here, starting from microstrip, coplanar, waveguide, strip line, parallel line. Various categories are there. So specifically, we will work with microstrip line, where the strip line is placed over the ground plane and are separated by a dielectric. This particular structure we will be working with. So let us click on this. So once we click on this microstrip structure, what do we find over here? See, you can find a microstrip structure diagram over here. Fine. Calculate Z0. Okay. So we want to find the width of the transmission line W. W is the width of the transmission line over here, such that the characteristic impedance becomes becomes 50 ohm. So whatever by default values are given in this, so let me calculate over here. So see, it is showing 80 ohms. Okay. So we have to design Z0 such that we can find the characteristic impedance to be equal to 50 ohms. Fine. Now, all the lengths will be taken in millimeters. So length units, you will find a drop-down menu where you have to select millimeter. Once you select this millimeter, see, okay. So different other things can be chosen. Now, specifically, I'm going back to the manual once again over here. We will take a substrate which is very commonly available and quite cheap in cost, and that is glass epoxy substrate, it is called FR4 substrate, whose relative permittivity is 4.3 or 4.4. Okay, you will find 4.4 or 4.3. Width of the substrate is width of the substrate is 50 ohm and length of the substrate is 100 ohm. So this is just a arbitrary value. You can take the width of the substrate as 25 millimeter and length of the substrate as 100 millimeter or 50 millimeter. That will not change the result, because always remember that characteristic impedance depend upon the width of the line, okay, not the length of the line. Fine. Height of the substrate is 1.6 mm and thickness is 0.2 mm, okay, and W is 2.93 mm, that we will find. Now there may be many questions that may be coming into your mind, that how all these things are chosen, what are those thickness and all, right? So very clearly over here, see, a strip line over the substrate is a metallic layer. See, a yellow kind of yellow shade kind of structure is shown over here. This is a metallic deposit, and at the other end of the substrate you will find a ground plane, right? So both are metals, say for example copper. Fine. Now this particular deposition must have some thickness, so I am talking about that particular thickness. Generally it is found that yes, since we are dealing with very high frequency, so we go for a very less thick deposition. Fine. See over here how I am editing all these things. Let us say the thickness is 0.2 mm. Fine. And as according to the problem, I have taken the length of this substrate is 100 mm. Fine. And the height of the substrate is 1.6 mm. Achha. Relative dielectric constant, you can find a drop down menu over here. It is FR4 as I was talking about. So you have to scroll down and see where you find FR4. Let me see. Yes, FR4. See over here, many things are given. FR4. So whatever, we will take FR3. So though it is somewhat wrongly entered in the library, it will be FR4 actually, 4.3. So let us take 4.3 epsilon r. Fine. So 1.6 is the height of the substrate. Epsilon r is 4.3. At any point of time, if any students are unable to catch me, you can just interrupt me. I can repeat again, because you need to understand this, because we are having some physical feel of whatever we had learned in the theory part. Okay. So 1.6, 0.2, 100 mm is the length. Width of the substrate is okay. Width of the substrate is not given. So anyhow, length is 100. Width of the line is important. Fine. Frequency. What is the frequency? Frequency of operation according to this is 2.4 gigahertz. Fine. It is given 2.4 gigahertz. So let me 2.4 gigahertz. Let me set the operating frequency as 2.4. The weather is very loudly outside. 2.4 gigahertz. Okay. Now let me choose. See, very interesting. Width of this strip line. Let me choose the width of this strip line as 4 mm. See, 4 mm. It is explicit in the problem that it is mm, because I have already set the unit as millimeter, right? So let us calculate. See, once I set 4 mm, so you get an impedance that is 41.52 ohms. Now I will ask you one question. See, it is somewhat a hit and trial process over here. How do we arrive at Z0 is close to 50 ohms? Fine. Now shall I increase the width or decrease the width so that I can increase the impedance? Can anyone please?
Decrease.
Decrease the
Sir,
width.
decrease the width.
Yes, decrease the width. Okay, let me decrease the width. Let me make it 3. Let us calculate. Yes. So 49.34. So we are very close to 50 ohm. So let me decrease to 2. Let me see. See, it has increased. So we have to increase the width a bit. So it is, if I set it to 2.9, it will be almost equal to 50.29. So we are very close. 2.93, almost it is exactly 50 ohms. So we have to keep it as a record that 2.93 is the width of the line for which we get the characteristic impedance as 50 ohms. Fine. Achha. One more thing we have to keep in mind over here, this epsilon effective 3.2. See, epsilon r is 4.3. Try to understand this very interesting thing. Just a very short, a brief discussion I will make. What is the difference between this epsilon r and epsilon effective? See, this strip line will have some electric field distribution. Why? Say if the strip line is at higher potential and this ground plane is at lower potential, what will happen? The electric field line will start from this higher potential and it will terminate at this lower potential. So that electric field is intact within this substrate. But at the edges, what will happen? Edges of this strip line, the electric field will go into the air. See the movement of the cursor, right? I'm not going to the paint again. So it will go outside the air and it will go in the substrate and then it will terminate over here. Now, had the transmission line being inside the substrate, that means this particular transmission line, if it is inside the substrate, then whole electric field would have been confined within the substrate itself. But it is not happening in this microstrip structure. Some portion of the electric field is in the air and some portion is in the substrate. So it is not completely governed by epsilon r of the substrate, but it is also governed by the epsilon r is equal to 1 of the air. So there must be some effective electrical characteristic. That effective electrical characteristics is given by this epsilon effective. So there is an empirical formula of epsilon effective. Hammerstead formula, it is said. It is epsilon r plus 1 by 2 plus epsilon r minus 1 by 2 into 1 plus 12 into h divided by w whole to the power minus half. A very big empirical formula. I always work on this. That is why I remembered that, right? So you can type in Google or any standard textbook, you will find that empirical formula. So this particular software has the advantage of calculating that empirical formula also, right? So I just showed you the importance or utility of this software. So epsilon effective is noted down. So I hope some one of you are noting it down, or every one of you are noting it down. And width of the substrate is also noted, I believe, 2.93, right? So with this, we will start the design, right? So first of all, I will demonstrate that how this 50 ohm transmission line, after being connected with a load of 150 ohm, will give a very reduced, will give a huge reflection. How do we understand? We will not get a desired S parameter curve. So let us try to start the design. Okay. So this is, once you start the application, CST Studio Suite, somewhat you will get a window like this, right? So there you will click on this project template.
Excuse me, sir.
Yes.
So I have the 2019 version as you gave in that Google file. Is this that one or it's 2021 version?
This is a 2019 version. See, to 2020 version to 2019 version is almost similar with small added feature that will not create any problem. Okay. All the things are same. Small visual difference is there. Right. So anyone working in 2020 version or 2019 version will not have any problem with the understanding. Understood? Okay.
So at first you clicked on which button, sir? Just to show. Actually, the software is slower a little.
See, this project template.
Yes, sir.
So I have already sent you the manual. So I prepared the manual. Each and every steps are taken screenshot and then attached, and then I had sent to 2019 version. So you can take the reference of that particular manual also. First of all, just see the flow. We are going into new template, right? Right. So here you will find many applications: microwaves and RF optical, EDA, EMI, EMC, particle dynamics, statics, low frequency, whatever it is. Many applications are there. So particularly we will be choosing microwaves and RF optical, right? So let us click in this. Again, once you click in this microwaves and RF optical, you will find various applications. So strip lines, the most easiest thing to design is under the application of antennas. So let us click in this antennas. So first of all, I clicked in this microwaves, then antennas, then click on what happened? Click on next. Okay. You will find many applications again. Particularly click in this planar because we are going for a planar structure. Then next. Okay. There are two solvers. Let us not discuss now at this particular stage what is the advantage or what is the utility of different solvers. So we will stick with time domain solver, right? Time domain solver. We will not change the default units where dimensions is in millimeter and frequency is in gigahertz. Let us click next. Okay. Now we want to see the frequency window. We want to set the frequency window. Why it is required to set the frequency window? Because otherwise we cannot find the sharp resonance. So we are designing a 2.4 gigahertz. So let us.
Excuse me, sir.
Yes, tell me.
So we will select time domain.
Yes, time domain.
Okay.
Time domain. Time domain. So that frequency window, you can choose it from 1 to 4 gigahertz. Okay. So you can choose 1 to 10 gigahertz also. Unnecessarily it will run. The runtime will be increased. Since we are dealing with a frequency at 2.4 gigahertz, so it is well within that in this particular window that I have chosen. Okay. So we will not monitor all these things, whatever is being displayed over here, E field, H field, far field, power loss, whatever it is, we will not monitor. Next, and then finish. Now, once you finish with this particular once you set this particular template, what I say, this template, then your window will look like this. It's taking some time for initialize. Okay. Let us give that particular time. Okay. More or less, maximum of you will visualize the window like this. Fine. More or less. You can save. I have already tried with this, so I have saved in many ways. Anyhow, let me save it as 1. Okay. Right. Now let us initiate the design process. Your window will look like this. So first of all, you will go to modeling. See, designing this particular structure requires a very good visualization of coordinate system. As you can see, the structure is a 3-dimensional structure. We are trying to design in this particular environment, and we require a very good understanding of the coordinate system. The reference is XYZ as shown in the right hand side of this particular window. Okay. I hope every one of you have opened this window. Please tell me whether I shall proceed or not. Shall I proceed or not?
सर
See,
आपने जो सर फिनिश किया था उसके बाद एक प्रॉब्लम आ रहा है सर.
What problem?
ये वाला पेज नहीं ओपन हो रहा.
What problem you are facing?
Can I share sir?
Okay, share. What problem? Share your screen.
It's showing sir. It's showing.
Application exe has encountered a problem and need to close the current worksheet. You can try it once more. Click on OK. Click on OK. And again, create the project template. No. Create project template. Microwaves, yes. Antennas. Next. Patch. Next. Time domain. Next. Next. 1 to 4. Next. Finish. Wait. Now it is okay, right?
Yes sir. Yes sir. Thank you sir. Nice sir. No sir.
What is happening?
Same page open.
Click on this.
Sir, same problem.
Okay, just go through the process. I think rest of you are have already opened this, right? Aniruddha, I will come back. Okay, I don't know why this problem is occurring, so
Okay, sir.
we have to troubleshoot, right?
Sir,
Yes.
sir, even I am going through the same trouble.
Every
May I
one of same problem.
Yes, sir.
Every one of you are going through the same problem. The rest of Snehashish, Satyam. Okay, you can share the screen. Let me see.
Yes, sir. Sir, is it visible?
No, not yet.
Sir, I've shared the screen.
It is not yet visible. You have not shared the entire window. I think so. Only the screen. Share the entire window so that it is visible to.
Yes, I have shared the entire window.
Is that screen
Uh,
visible to you? No,
this
it is
one.
not. It is not visible to me.
Sir, can I rejoin once then?
You can rejoin. No problem.
Okay, sir.
But I want to ask some more students that whether you are facing the same problem or not, or your template is okay working.
It is okay, sir.
Sir, it is okay. Okay, sir.
Okay, okay. Then I think they can reinstall the software and I think it will run maybe. Okay, fine. Let me continue. Okay. I think my screen is visible to everyone. Yes. Why I'm asking every time, because in Zoom platform it is very quick, but in Google platform it is not that much quick. Anyhow,
Yes.
so let us start the design process. And
Sir, excuse me, sir.
yes, you have rejoined.
Yes, I've rejoined and I'm trying to share. There's some problem. I'm not understanding what's the issue.
Okay, you share the screen. Share the screen. What problem you are facing? Let me see.
Yes, sir. I'm joining. I'm sharing the whole window, but it's not happening. I don't know why.
You ask some of your friends whether they can help you in this.
Okay.
In the meantime, let us.
स्क्रीन को सिलेक्ट किया है, सिलेक्ट करके शेयर कर फिर।
हाँ, वैसे ही किया है जैसे बाकी लैब्स में करते हैं वैसे ही किया है. Okay, sir, you continue. If I figure out something, I'll let you know.
Okay, let me complete this one. Then you follow the steps. Okay, then you will show me the problem. I will definitely give you some extra time in solving the problem. Okay.
Yes, sir. Yes, sir.
Okay. Okay, fine. Let us start the design. So we had already found the parameters. Now, first of all, I will start with designing the substrate here. How do we design the substrate? See, in the top, you can click in this modeling. Okay. So after you click in this modeling, you will find a brick option. So click on this brick. So once you click on this brick, see one message will be popped up. According to this, you can press escape. So once you press escape, a small window will open. So there you can type substrate. You name this as substrate because first of all I am designing the substrate. Now try to understand this. Before I proceed with this x min and x max, y min, y max, z min and z max, what is this? What is the meaning of this? See, I'm going to this particular window once again. See over here. So it is a cuboidal kind of structure. I think you will agree, right? So obviously the leftmost point, if it is, I mean, if the horizontal direction is the x direction, then one point will be x min, another point will be x max. That is what is meant by that. Say the longitudinal direction is the y direction. So obviously it will have a y min and y max. So that is what it means. Fine. Now according to the problem that I have taken over here, I have chosen the dimension of the substrate to be 100 cross 50 mm. Okay, width of the substrate is 50 mm and this length of the substrate is 100 mm, right? And height of the substrate is taken to be 1.6 mm. If you so, let me go to this. See, I want to
So
make
maybe
it symmetric.
so, excuse me, sir.
Yes, yes.
So may you please once tell how do we get this? That is.
See, you go to modeling, right? See over here, there are many options. At the top left, file, home, sorry. What happened? Some problem. Wait. Just let me reopen. Okay. So how do we get this? See, you will find various things over here: file, home, modeling, simulation. So over there you will find modeling, right? So once you click on this modeling, see there you will find a brick, because you are trying to do construct a structure of brick kind of you are trying to construct a brick kind of structure, right? So click on this brick. So once you click on this brick, a message will pop up in this window. Press escape to show the dialog box. So in your keyboard you will press escape. So this small window will pop up. So there you can rename this as substrate, as you are designing substrate. Now, according to the problem given in the manual, I want to align the substrate such that the width is along x-axis and the length is along y-axis. So it is not a hard and fast rule. You can align the substrate such that width is in different axes, no problem with that. That depends upon the user's convenience. So according to my convenience, I find it convenient to align the substrate such that the width is along x-axis. Now the thing is that if you look into the manual, you will find that the width is 50 mm and the length is 100 mm, right? So you can choose in many different ways. You can type x min equal to 0 and x max equal to 50, no problem with that. So in that case, see the movement of the cursor. You will have a starting point from the origin and it will go towards the positive x-axis, no problem. So, but I want to make the structure symmetric, right? So I am choosing the width 50 mm as minus 25 to plus 25. That means half of the substrate is in negative axis, x-axis, and half of the substrate is in the positive x-axis. Okay, I hope you have understood, right? Now, I want the substrate to be aligned along y-axis. That means length is along y-axis. So according to the question, the length of the substrate is 100 mm. So let us choose y min is equal to 0, or you can choose y min is equal to minus 50. That is according to your choice. So I am choosing y min is equal to 0 and y max is equal to 100. Okay. Fine. Now I want the thickness of the substrate to be along z.
Sir?
Yes.
Sir?
Tell me.
So we can set x min equals to 0 and x max equals to 50 also.
Definitely, no problem with that. Definitely.
Okay.
But if you set that one, then you need to do some extra calculations that I will show you. Okay, so that is why I am doing it in the most easiest way. That is no problem. The thing will be same. No problem with that. Okay, fine. Now thickness of the substrate is 1.6 mm, right? So I am choosing the thickness of the substrate, or say along z-axis. Okay, so let's say z mean is equal to 0 and z max is equal to minus 1.6. Can you tell me why I have chosen minus 1.6? Because I want that the substrate is along negative z-axis. Try to understand. Okay, now.
Yes, sir.
Okay, now see, what is the material of the substrate according to the problem? Check the manual and tell me.
FR4.
FR4, okay. So by default, the material is vacuum over here. So we cannot keep it like this. So you have to go with this, click on this drop down menu, and you will find load from the material library, right? So once you click on this, your material library will open, and there you can find FR4. See, FR4, it is loss free or it is lossy. Obviously, the practical materials are lossy and the ideal materials are loss free. You can try with lossy. I am showing you with loss free. Fine. See, FR4, at the bottom side of this small window, you will find the properties of this particular material listed over here. Epsilon is equal to 4.3. You load this. So once you load this, the material FR4 is chosen, right? And once you click on this OK, then your substrate is built. You can set the view of this substrate. See, you can click on this view. There are many options over here. There is an option called reset view. Click on this reset view. Yes.
Sir, you
Yes.
selected loss free or lossy?
I have chosen loss free.
Okay.
All of you can choose loss free. Yes, Pushpa madam, you wanted to say something.
हाँ सर, मटेरियल जो है ना वहीं पे क्लिक करना है तो
हाँ. Yes.
फिर क्या आ रहा है न्यू मटेरियल लोड फ्रॉम
No. Yeah, load from material library.
हाँ वो क्लिक करने से
FR4, you can find FR4 in the library.
वो वाला तो नहीं आ रहा है मेरा 99.5 लस्सी
You can choose that one. But also you can define new material. New material, you will find new material. There you can enter epsilon r is equal to 4.3. That will also work, no problem. But it is already in the library. That is why I have chosen. Okay.
Excuse me, sir.
Yes, excused.
Yeah. Sir, can we enlarge this window? Actually, the canvas space is quite, small. So, is there any way?
Yes. See, there is a view. Okay. See, or you can minimize this one. See, you see the movement of my cursor. You can set this, or you can set this like this. Fine. There is an option called reset view. First of all, what you will do, from this drop down menu, click on this reset view. You will get the view like this. If you want to zoom, then you can click on this zoom, and then left click your mouse and select like this. You can enlarge. Okay, there are many options. So also you can rotate. You can rotate like this. See, rotate. You can rotate it like this. So I will show the utility of this in a short while. Okay. See, you can rotate. No problem. See, as you have asked the question, you can please switch off your mic. It is created.
Yes, sir. Yes, sure.
Okay. See, as I was talking about, that the thickness of the substrate is 1.6, and it is oriented in the negative z-axis. So you can have a feel that how it is in the negative z-axis. You can see the small thickness over here, see, it is along, okay. Reset view. It is like this, fine, along negative z axis and all, thickness. You can find many options. See, there will be an option called pan. So once you click on this pan, then left click, you can take the structure anywhere you like, fine. So you can explore upon this view. See, over here you will find many other default options like perspective, front, back. So once you click on this perspective, you will get a view like this, right? Again, you if you want front, it will be like this. Then if you want top, it will be like this. So you can explore on this. Okay. Now the substrate is done. Now I'm going back to the structure again. See, there must be a ground plane at the bottom. That ground plane is covering a whole face of the bottom of this substrate. So I have to construct accordingly, right? So how do we construct the ground plane? See, again you have to go to modeling. Then using the same process, you have to click on this brick. Then press on escape. Now, since you are designing ground plane, so let us type ground over here. Right. First of all, let me choose this material. After that, I will set the dimensions. So material. So once you click on this material, see the ground plane is not substrate again. Okay, it is a metal. Right. So you can choose copper, gold, whatever it is. So let us choose PEC. PEC indicates perfect electric conductor. What I said, perfect electric conductor. Right. So let us take this perfect electric conductor. So it includes all the ideal properties of the conductor. So that is why I have chosen PEC. If you want to go with the practical design, you can again go to the material library. You can choose copper, gold, tin, whatever you want, right? So this PEC is chosen. Now, according to the structure, where the ground plane will lie, it will lie at the bottom part, not at the top part. Right. So carefully you have to choose the dimension. How? See, everyone look into this. Right. X min will be minus 25. X max will be plus 25. Y min will be 0. Y max will be 100. Same as we had taken for the substrate because it is covering the full face of the ground plane. Right. Now, Z min will not be 0 because I have chosen the thickness of the substrate to be 1.6 mm because it is most commonly available, right? The thickness of the substrate starts from Z equal to 0 and it ends at Z is equal to minus 1.6. Try to understand. That means it is along the negative Z axis. At any point of time, if you feel some difficulty, you can prompt. Again, I am telling you. Okay, the substrate thickness starts from Z is equal to 0 and it ends at minus 1.6. Okay, so it is Z is equal to minus 1.6 from where we will start the ground plane. So obviously Z min will be minus 1.6. I hope you have understood the logic. Now, what will be the thickness of that deposition? Thickness of the deposition is 0.2 mm, as we had taken in this AppCAD software, 0.2 mm. So it will be Z max will be minus 1.6 minus 0.2. Okay. Let's click in this OK button. Okay. Now go to view. Check. See, you are trying to see the back. So I will click on this back. See, your ground plane is constructed. Okay.
So how much you took the Z max, sir? Will you take Z max?
One more thing. Okay, Z max. See, at any point of time, if you want to edit the dimension, how do we edit the dimension? I am showing it. It will answer your question also, and one more information will be added, right? In the left side, you will find one navigation tree. So in this navigation tree, you will find components, and under the components, you will find ground and substrate, right? Now, double click on this ground. See, a window is popped up, history tree. Okay. So component ground, double click, check, see what is the dimension I have taken. It is minus 1.6, Z max is minus 1.6, minus 0.2. Why? Because thickness of the deposition is 0.2. Okay.
Okay. Yes.
Okay. So it may happen that anytime you try to construct that, and some values need to be edited. So how do we edit that? So you can go to this navigation tree, double click on the component, you will find this history. There you can edit, no problem with that. Fine. Okay. So till now we are going in a correct way. So there is no requirement to edit. Component view. Fine. Now ground plane construction is over. Now we have to construct the strip line. Okay. So how do we construct the strip line? See, strip line is at the top part of the substrate or at the opposite side of the ground plane, whatever you say. See, again, same process, go to modeling, click on this brick, press escape. Over here, just type strip line. Fine. Now, can you tell me, using that AppCAD software, analysis and synthesis of transmission line, what is the width of the line that we had got? Tell me. I believe that everyone has noted it down.
2.93.
2.93. Okay. So 2.93 is the high width of the strip line. So I will construct the strip line exactly at the middle. So how do we choose X min and X max? Half of the strip line must be in the negative axis, half of the strip line must be in the positive axis, isn't it? Exactly in the middle if I want to construct. So what I will do, what you said, 2.93. I will do like,
1.22 plus
yes,
1.2.
exactly. So exactly. So, or you can write it like this, minus 2.93 divided by 2, that will give you the same result, plus 2.93 divided by 2. Why I have chosen like this? Because some small mathematical calculations are also inherently done in this window. You always need not have to calculate and write it down. Okay, that is the advantage. So 2.93 divided by 2, here X max 2.93 divided by 2. And length of the line will be same. It will start from y equal to 0 and it will end at y max equal to 100, right? Can you tell me what will be Z min and Z max, provided the thickness of the deposition is 0.2? Tell me. Let me listen from you. It may be wrong, no problem. I don't mind. But
Minus 1.6 by 2 to 1.
No. Anyone else?
So minus 1.6 to minus 1.6 to 1.
No. Actually, the thing is that is why I asked you. Okay. See, the substrate started from Z equal to 0. And it ended at Z is equal to minus 1.6. Try to have a feel of
0.2.
dimension. Yes. So Z min will be 0 and Z max will be 0.2. Understood? Is the thing.
Yes, sir.
Yes. So once you do this, see, material is PEC. You need not have to change that. If at all it is changed somehow, you have to keep in mind that it is PEC. Change it. Otherwise, again, you have to reconstruct. Okay. So strip line, click on OK. So a strip line is constructed like this. So your 50 ohm strip line is constructed. Now, what next? See, 50 ohm microstrip line with a load of 150 ohm. So you have to connect a 150 ohm load. See, here lies an important concept. How do we connect a load over here? A lumped element load. A lumped element, a resistor you are connecting, right? So how do we connect that? All of you, please follow this step. This is very important. I mean, a bit critical, not that much. Okay, so what you will do, you have to adjust the view first of all. See, click on this view, and I want to zoom something. What I want to zoom this particular end, right? Now, once you zoom this particular end, you can see that is very well visible. That small thickness of the line and substrate and then ground and all these things are very well visible, right? Now, where you will connect the load? Anyone tell me? Okay, let me tell. It will be connected between the strip line and the ground plane. Do you agree with this? Will be connected between the strip line and the ground plane. Definitely. Okay. Okay. Now, how do we connect that? First of all, we have to select. Now, for that, you need to go to simulation. Yes, you need to go to simulation. Then, at the top, you will find something called PICS. P-I-C-K-S, PICS. Now, when you click on this drop-down menu, there will be various options. For this, I want to select one edge. For that, I have to select this one, pick points, edges or faces. So let me click on this. So once you click on this, now if you move the cursor at different points, see if you move the cursor over here, this is selected. The face is selected, and then again if you move to the end, edge is selected, or this particular thing is selected like this. So you want to select one edge. This particular edge of the transmission line. Right? So it is red now. Once you place the cursor over here, it is red now. Just double click. Just double click. So once you double click, it is selected. Now what you will do, again go to view. Just directly click on this back. So once you click on this back and then wait. Okay. Once you click on this back, then the back side of the structure is, the back side is nothing but the ground end, right? Now, as the lumped element need to be connected between the transmission line and the ground plane, so your ground plane also need to be selected. In a similar fashion, if you go to simulation and click on this pick and pick face, place the cursor over here in the ground plane, it will become red. So once you double click, it will be selected. So the face and one edge of the transmission line is selected, right? What is the purpose of this selection? Because it will automatically understand that the terminals of the lumped element will be connected between these spaces, right?
So you show the previous step. Just now what you did. These boxes are coming.
What you will do, you will click on this picks, fine. So a drop down menu will come, then click on this pick.
Yes.
So once you click on this pick, then place the cursor over the ground plane. You will find that your ground plane is red. Fine. So once it is so, you just double click, placing the cursor over the same position. You will find this boxes kind of thing. This boxes kind of thing itself indicate that the whole ground plane is selected. Okay.
Okay. Yes, sir. Yes.
Okay. So once you are complete with these particular steps, what you will do? Yes. Go to left. the navigation tree, you will find one option called lumped elements. Have you found that one? Okay, so once you find this lumped element, right click. Once you right click, it will prompt you click on one of the option. Click on the option new lumped elements. So once you click on this lumped element, then this particular window will pop up. By default, see, it will be a series RLC circuit. So how do you actually choose only R without L and C? Simply make the values of L and C 0 and 0. See properties, L is equal to 0, C is equal to 0. According to the problem given in the manual, the R is 150 ohm. So just click edit it as 150 ohm, and no other thing. Nothing is required. Only 150 ohm, and set L equal to 0 and C is equal to 0. Okay. You can edit this particular name. You can edit the name as load, or you can keep it as it is. That is your choice. Name is load. Okay. Then let us click OK. So once you click on OK, your load is connected.
Sir, can you please show how you got that box lump element?
Yes, under the navigation tree, you will find lump elements. Right? Can you see the placement of the cursor over here? See, if search in the left side of the window of your laptop, you will find navigation tree. In the navigation tree, you will find lumped elements. So once you find these lumped elements, just place your cursor over the lumped element and right click. So once you right click that lump elements, you will, some options will open, right? Click on this new lump element, the very first one, and this particular window will pop up. Just the default values are R is equal to 0, L equal to 0, C equal to 0. Make R is equal to 150, simply 150. And click on OK. Your lumped element will be constructed, right? I hope you have understood. Yes, let us see the perspective view. See, your load is connected. Now, see the construction of the structure is what? 50 ohm transmission line, and then what I say, load. All these things are over. Fine. But you need to feed the transmission line. That is also a very important step, right? So how do we feed the transmission line? Let us see. See, observe these steps. Up to this, I believe that no one has any problem. At least you have understood. And all the steps are very, I have tried to explain each and every steps in the manual. So you can go through that also. And assignment is also provided to you. Wait.
Excuse me, sir.
Yes.
So this cuboid box actually vanished away. I don't know how it got vanished. Means only I have the this man plate, strip line, whatever. But this box, the cuboid box inside which we are getting a greenish area. So this box is not coming now.
No problem with that. See what I'm doing.
Yes.
Go to the top.
Yes, sir.
See, there one view option, top left corner. See the view option. So you uncheck this bounding box.
Uncheck. Yes, sir.
You click on OK. Now it is vanished for me also. Okay. You can check that one. It will.
Okay. Okay, sir.
Okay. Now,
yes.
First of all, now the next step will be how to construct the waveguide port, right? Everyone, please have a very good attention in understanding this. Then we need to reset the view again. See the movement of the cursor, right? I have to feed the transmission line to this particular area. Okay. See the movement of the cursor. Fine. Now we have to select that portion of the transmission line. How do we select that? View option. Then click on this rotate option. Then left click your mouse and adjust the view like this. Adjust the view like this. Right. So that almost this kind of view is. This is the most easiest way to assign the port I am showing you. There are various other ways. Adjust the view like this. Now it is almost not visible. It's almost visible. Right. So what we'll do, simply zoom. What portion you need to
Sir, may you please do it one again?
see movement of the cursor. You rotate, you click on this rotate and left click the mouse and adjust the view accordingly. Yeah, I'm doing it once more. Fine, reset view. Perspective, everyone. See. You click on this view, obviously, then rotate. So click on this rotate, then left click the mouse. It will look like this. Once you left click, it will look like this. A symbol, this kind of symbol will come. That means a 3D, any way you rotate. So just move your mouse and adjust the view like this. Okay. Once you do like this, it is almost not visible. So to make it visible, just click on this zoom and left click. Okay. Now it is zoomed. So you have to assign the port over here. See the movement of the cursor. That means at this end of the transmission line. So for that, this small face need to be selected. 0.2 thickness that we had done, isn't it? So I am zooming it so that you can understand this is the 0.2 thickness. This need to be selected. So what is the selection process? The selection process is very same. It is exactly same. Go to simulation. Click on this pick and then pick point and faces and such and place the cursor over the face. It will be red. Double click to get it selected. It is over. There are various processes to assign the waveguide ports. Okay. Now what you will do, let me check whether it is available or not. Just hold on for a few seconds. Let me check one option whether it is available in the student version or not. Okay, that is what I am checking. One inbuilt macro is present. Just let me check. Okay. Up to this, is there any confusion? We have selected this small thickness of this transmission line, right? Now, what we will do at the top, go to home. I think it is not mentioned in the manual. Okay, it's this particular shortcut I am just showing you. You can write it down as a note. So after selected, after this particular thing is selected, go to home. Once you go to home, then at the extreme right you will find macros, right? You will find a drop down menu. There you will find solver. Okay, go to solver. There you will find ports. Okay, just give an arrow, home, then macro, then solver, then ports, and then calculate port extension coefficient. See, I'm giving you some time to write it down or take a screenshot. Home, macros, solver, ports, and then calculate port extension coefficient. Okay, click on this port extension coefficient. This window will pop up, right? By default, it is already chosen that microstrip line we are dealing with. See, we require this. See over here, this waveguide port, according to this software, is a rectangular kind of structure, right? So, what will be the dimension of this waveguide port? That will be automatically calculated from here, or else you need to calculate it manually, or else you have to give it arbitrarily. Okay. So if it is all the feature is available, why we will not use that? That is the thing. Now calculate. So once you click on this calculate, your port extension coefficient 6 is calculated to be 6.64. Okay. So either you can take this k equal to 6.64 from here, or you can calculate it manually. Then construct port from picked face. Click on this.
Sir, excuse me, sir.
Yes.
So from solver to F solver or what? Solver to ports.
From solver to ports.
Okay.
Solver to ports, yes. Okay.
Okay,
So
sir.
once you do with all those processes, your port is constructed. See, my window has become red, right? Actually, the port is constructed. I will just reset the view so that perspective. So you can click on different options over here in the view to visualize the structure according to your convenience. Okay. So I will request everyone after the class is over, you can explore upon all these things, right? So see over here, a thing is added, that is waveguide port. Just I will click on this 3D rotation to show you. See, this waveguide port is automatically assigned, right? Waveguide port, it is like this. So that is the easiest process. Another process is given in the manual. There are many other processes depending upon applications. I am not showing you now. So in this way, the whole problem is ready in this. I have not used the quarter wave line, but the whole problem is ready now without the quarter wave line. Now, let us see how this 50 ohm line connected to 150 ohm will lead to some unmatched, some huge reflection coefficient, right? That means what is expected? The reflection coefficient curve must not come beyond minus 10 dB, as I had explained in the previous class. So once all these things are over, what you will do? Go to simulation. Now go to setup solver. Do not change anything. Just start simulation. And let us see what is the result that is coming.
Excuse me, sir.
Yes.
So after port extension coefficient calculation, what do we have to do? Like after we press the calculate button?
Then after the calculation button, what is another button is given? What is that? Create something like that. What is given?
Sir, construct port from
Yes.
picked face.
You click on
Sir,
that.
but the option is not coming, sir.
So you have not calculated, selected. That is why you have not selected the face. You might not have selected the face. That is why the option is not coming. Okay. Now you can see. You select the face, then the option will come. Okay. Now see, the simulation is over. Go to left. Navigation tree. Under this navigation tree, you will find 1D results. See the movement of the cursor. Everyone see. All these things are also given in the manual. Okay. 1D results. You expand this 1D results. Many options, many things are calculated. So what is most important is S parameters. S parameters. Expand. S11. As I had discussed in the previous class, this indicates the reflection coefficient. So once you calculate this, some see 2.4 gigahertz is the frequency. So over here, you can see some absurd kind of curve is coming, and the curve is not going beyond minus 10 dB. How? See in the vertical axis, at 2.4 gigahertz, it is maximum up to 6.2 or 6.25, like this, minus 6.25. So there is a huge mismatch. Have you understood? This is a physical realization. That how do we understand that huge mismatch is there? Your reflection coefficient is very high, right? The way the power is not fully delivered to the load. That is the thing. So we require a quarter wave transformer. Okay.
So can you once again show how to like select the phase and calculate the coefficient?
Again. Okay. I will delete this code. Again, I have to simulate. This is those who have not understood, please pay attention. So how do we select the phase? You need to give the input through this, right? So click on this view, then enable this 3D rotation, then enable this 3D rotation and rotate it according to your convenience. Click on this zoom, then zoom on this. This small face need to be selected. How do we select that? Go to simulation, then you will find peak face. This small face need to be selected. You have to place the cursor accordingly. Okay, so this small face is red now. So once it becomes red, double click, it gets selected. Okay, now your job is over. Now let the software do the job. Home, then macros, then solver, then ports, then calculate port extension coefficient. Now see, to calculate 6.64 is coming as the port extension coefficient. Construct port from pick face. Click on this. I think it is constructed. Yes, it is constructed. Now you can reset the view according to your convenience perspective like this. It is okay. Okay, I am re-simulating for you. Now see the S parameters. So 2 times I have simulated. Those who have understood, those who have not understood, I think they have already understood, right? So this is the S parameter. Huge mismatch. How we can understand that? It is well above minus 10 dB. So obviously there is a huge reflection. So we have to design a quarter wave line. Okay. Now go to this. Let us go to the manual again, right? This is, see, I have devoted a huge amount of time in explaining this in the form of a manual. Okay. So, wait, something has come up. Okay. Now we have to, so this kind of curve we have already got in the after the simulation is over, right? So we have to match using a quarter wave line. So for that, what we need to do, see, design of in the next step, design of quarter wave transformer for matching a 50 ohm transmission line. So your Z0 is equal to 50 ohm and ZL is equal to 150. Clear? So you have to take a quarter wave section of a transmission line such that the characteristic impedance of that new line is under root Z0 into ZL. I have already calculated it, so you can verify. 86.6. I will give you a different problem. Obviously, I have given some different problem in the as a report. So you will have to calculate. Everyone has to calculate it, right? So Z0 dashed is equal to 86.6 if you invoke this particular formula, right? So that is Z0 dashed. So you have to take 86.6 ohm characteristic impedance. Now, length of the transmission line is quarter wave. Quarter wave means lambda by 4. And what is this lambda? Lambda is actually lambda g over here. Lambda g divided by 4. Guided wavelength. Since we are not using the free space model, right? So because we are using substrate over here, so we have to calculate lambda g. So how do we calculate lambda g? If you look into the top part of the manual, I have very lucidly explained over here what is this lambda g. This lambda g is equal to lambda naught divided by root under epsilon effective. Epsilon effective is already obtained using the AppCAD software, right? 3.2, something like this. Or you can use that Hammerstedt formula. Doing some manual calculation will give you the same result. So lambda naught, first of all, you calculate corresponding to 2.4 gigahertz, because according to the problem, we are designing it for 2.4 gigahertz. Let me see. Okay. See, operating frequency is 2.4. So first of all, you have to calculate lambda naught corresponding to 2.4 gigahertz. Then you have to divide that lambda naught with root under epsilon effective. You will get lambda g. So once you get lambda g divided by 4, that will be your quarter wave line length. Okay. Everything is very well mentioned in the manual. I have already calculated for this particular problem. You will have to calculate for your own frequency that is already given in the report. Sorry, in the assignment. Length of the quarter wave transformer according to the steps that I had discussed is 18 mm. So please take a note on this. Length of the quarter wave line is 18 mm and characteristic impedance is 86.6 ohm. Characteristic impedance is 86.6 ohm. Try to understand. So if the characteristic impedance is 86.6 ohm, then what will be the width of the line? So again, you have to take the analysis and synthesis of transmission line. Let us decrease is 1. Let me take 1 and calculate. It is 82.33. So let me take 0.8. It is 89.86. See, 86.86. Exactly we have got. So take a note of that the quarter wave line will have a width 0.6 mm. And the length is already calculated. What is the length? Length is calculated to be 18 mm. Take a note of this. When I will design, you will help me so that I will not have to switch over the window. Okay. Okay. Now, what I will do, I will go to this CST Studio Suite software. Again, since you have to paste many results, so you will not edit on this particular project. Rather, what you will do, you will save as, say, 1_quarter wave. 1 indicates experiment number 1. That is your nomenclature according to your convenience. Now, in the second project, we will edit this. So what I will do, first of all, I will remove this load, right? I will remove this load. Let me remove this load. Simply, how do we remove this load? See, go to this navigation tree, then lumped elements. Under this lumped elements, you will find, you click on this lumped element, see, expand this lumped elements. Click on this load and simply press delete from the keyboard. See, it will get deleted. Okay, let me delete this. It is deleted. Tell me, what is the length of the transmission quarter wave line? Tell me, anyone?
17 mm.
Yes, 18 mm, 18 mm. So,
Yes, sir.
see the movement of the cursor. See, I have to append an 18 mm 86.6 ohm transmission line over this. Isn't it? I have to connect over this. Right? For that, what I need? I need to extend this substrate length to 18 mm first. Otherwise, the strip line will hang. Okay. So I have to extend it first. How do we do that? Click on this, see the movement of the cursor, go to navigation tree, click on this substrate, double click in this, then double click in this brick as we are editing it. Length of the substrate was 100. Now I want to extend it further to 18 mm so that it becomes 118. So either you can write it like this, 100 plus 18, or you can write it like this. No problem with this. So whatever, if it is some big calculation, it is always, it can be written like this, 100 plus 18. Okay. So you can preview, it is increased. Okay. The substrate is increased. Length is increased. Now, I have to construct a quarter wave line. So for that, again, I have to go to modeling. Then over here, you will find brick. Then same process. Click escape. Just write it over here. Quarter wave line. What will be X min and what will be X max? What is the width of the line that we have got? Tell me. Quarter wave line.
0.86.
0.86. So simply, X min, I will put 0.86 divided by 2, or you can directly write 0.43. 0.86 divided by 2, X max. Okay. Y min, what will be Y min? Let me listen from you. See, I want to construct the quarter wave line exactly from this particular top of the original transmission line. So we have to choose Y min accordingly. So if I am not wrong, it should be 100, right? Because for this original transmission line, the bottom point was y min equal to 0 and the extreme point was y min is equal to 100, because initially it was 100 mm, right? It is from this 100 mm point we are appending the quarter wave line. So y min in this case will be 100 and y max will be 100 plus 18. Okay. Z min and Z max will be as it is 0.2. Let us choose material to be PEC. Okay. And then preview. See, the quarter wave line is constructed. Now it is constructed. See, I will show you one thing. Let me zoom it. See, it is, these are constructed, no problem with this, but these are not connected. Water wave line is constructed exactly from the top, and whatever length and width is required, it is constructed, but it should be connected with the original transmission line to which load was connected, right? So how do we do that? We have to connect the original strip line with the quarter wave line. How do we do that? See the process. Click on this strip line. Go to left in the navigation tree under component 1. Click on this strip line. Okay. Then go to modeling. Click on this strip line, then go to modeling. Then you will find Boolean over here. Boolean option over here. Click on this drop down menu, then add. Then again go to left in the navigation tree, click on this quarter wave line. Okay, then press enter. Actually, you have done Boolean addition. Now these two are connected. Fine. Connection is over. Now we have to reconnect the
Sir,
load.
can you show it once again?
Again, why you are not seeing it? See what I have done. Go to strip line. Then there is an option called Boolean. Okay, under modeling, you will find an option called Boolean. So there you will find a drop down menu. Just click on this add. Then take your cursor. What you want to add? The quarter wave line. Click on this quarter wave line. Then press enter. Then these two are added. These steps are very well shown in the manual. Okay. If you forget, you can refer to the manual. That is why I prepared the manual. Okay. I hope you have understood. Yes or no?
Yes, sir.
Okay. Now the next step will be reconnection of the load. That is 150 ohm, right? So the reconnection of the load will be exactly similar to what we had done previously. Okay. Let me reset the view. Okay. Now, the load will be connected between this strip line and the ground plane. So we need to, what we need? We need to select the edges, right? So for that we have to zoom according to our convenience, okay, such that this small edge is visible. Same process, go to simulation and then pick points, edges or faces, place the cursor such that one edge is selected, double click. Now again go to view. You can just directly select the back. Okay, one more thing I forgot. See, your ground plane also need to be accordingly adjusted, right? So what you will do, just click on this ground plane. A history tree will pop up. Now you will tell me what adjustment I will make. Anyone please tell me what adjustment I will make, such that the ground plane covers the whole back face. Anyone tell me?
Wavelength becomes 100 plus 18.
Very good. Simply make it 100 plus 18. Okay. So it is like this. Now, what I was talking about, this ground plane also need to be selected. So for that, again, you need to go to simulation, then pick points, faces, edges, place the cursor such that it becomes red, double click. Now it has got selected, right? So once the edge of the line and the face of the ground plane are selected, what is our next step? Go to left, and under the navigation tree you will find lumped elements. Click on these lumped elements, right click, then you will find new lumped elements. So once you click on this new lumped elements, you will you know the process. I'm not repeating once more. Edit the value of R as 150 ohm and click on this. Okay, your element is added now. Now addition of port and all those things are not required because it was already done before and you saved as the project. Perspective view. See, all these things are there. Now let us see what is happening. Okay, so I hope you have understood the process, how because we had learned theoretically in our previous semester. Now actually what we need to do, I think you've got a feel of that, right? So disconnecting the element, then connecting the lumped element to a quarter wave line, how it improves the result, right? So what you will do, go to simulation, then set up solver, then start simulation. Okay, the simulation is over. Same process, navigation tree. Under this 1D results, see 1D results, you have to populate this 1D result. That means expand this 1D result. Then again expand this S parameter. See the portion of the curve. You can view 1D plot. See, this particular portion is below minus 10 dB. So you can see the frequency range where you can find a very good matching, because minus 10 dB was the reference point. But it has got curve markers. Okay, you can see minus 2.4 gigahertz, or sorry, 2.4 gigahertz. This is the frequency. This is minus 10 dB. From 1.5 to say over here 3.4, the portion of the curve is below minus 10 dB. So you are getting a very good matching within these frequencies. Okay. So impedance matching using quarter wave transformer is over. If you have any question, you can ask me. Have you found this session interesting? That is the main purpose of my teaching for long 2 hours. Have you had a feel of what is happening in this quarter wave transformer?
Sir, may you please show the change in the ground part which you've done later?
Go to this ground, you will find a history tree. Here Ymax, it was 100. So for adding the quarter wave line, I had to extend the ground substrate to 18 mm, right? So accordingly, ground plane also had to be extended up to 18 mm. So that is why I added 18 mm over here, plus 18. That is the only change. Okay. Yes or no? Have you understood?
Yes, sir.
Actually, I have what is this? See, the assignment is also allotted to you, and you have to submit it by next week. Next week means by Monday you have to submit it, Monday midnight. Okay, before your next lab is starting. It is, and the manual is also prepared such that you can understand each and every steps very clearly. Also, I have given you a 2-hour-long demonstration of this. I hope you will be able to perform the experiment. So now see how your problem will be different. Each and every student will be given or are given different tasks. Why? See, this is same. To design a quarter wave transformer for matching a 50 ohm microstrip line. That means you have to match a 50 ohm line. That is okay. But in the manual, I have given 2.4 gigahertz. Okay. So here also you can choose 2.4 gigahertz. No problem with that. Okay. You can choose 2.4 gigahertz. Nothing is mentioned over here in the task. So you can choose 2.4 gigahertz. It is same for everyone. But what is different? The load will be different. Okay. Load is like this. One, last 2 digits of your roll numbers. Say if your roll number last 2 digit is 00, then your load will be 100 ohms. If your last 2 digit is 29, then your load will be 129 ohms. So in this way, the problems are unique for different students. So I have made the report very simple to everyone. You did not have to write anything. You have to only type. Okay, so I have already sent you the report format. You have to edit. What you have to edit? First of all, say your roll number ends with 29. So here you will write 129 ohms. And rest other things, mathematical calculations. What are the different mathematical calculations? First of all, lambda g, epsilon effective. Okay, all those mathematical calculations that are shown in the manual, you have to do it again over here. And again, calculation of the characteristic impedance of the quarter wave line, that is root under Z0 into ZL. Okay, that will be different for different students. That will be different for different students. All those things has to be done under these sections. Then first design is microstrip line terminated with desired load. That means say 129 ohm. So there you have to just take a screenshot from the CST after you design that, and you paste it over here. Corresponding S parameter obtained, that you have to paste in this third section. In the fourth section, the design part of the quarter wave line, that need to be pasted from the CST, and the corresponding S parameter after the quarter wave transmission line is connected. Here also you need to paste the S parameter from the CST software. Okay. And finally, the conclusion has to be written by yourself. The conclusion should not be very straightforward. Whatever you have got, how much bandwidth you are getting, bandwidth in the sense, see over here, what is the bandwidth? Can you tell me what is the bandwidth? After your quarter wave transformer is designed, then what is the band of frequency in which you are getting good matching? Here, see, it ranges from 1.5 to 3.4 gigahertz. That means you have to find the portion of the curve that lies within minus 10 dB or beyond, below minus 10 dB. Okay. See, extreme edge is 3.37 and this is 1.5. So your bandwidth over here is the frequency range starting from 1.5 gigahertz to 3.37 or 3.38, whatever it is, gigahertz. So these are the important points that need to be extracted, right? And accordingly, you have to write the conclusion. And once you write the conclusion, finally, it has to be name, roll number section like this. You have to write. Then you need to convert it into PDF, not the Word file. I do not want the Word file. Very beautiful. Do not do it casually. It carries 2 marks. Do not lose that 2 marks. Okay. So it needs to be converted into PDF, and then you need to upload within the time. Right? Thank you very much. If you have any question, you can ask me.
Thank you, sir.
So the PDF file should be our roll number or name.
Preferably roll number. Yes, roll number. Your PDF file should be renamed according to your roll numbers. Okay.
Okay.
Okay. Pushpa, madam, I think you are present now. Madam, you please keep a track that students are submitting or not within time. Okay.
Yes, sir.
Okay.
So the first digit of the resistance will include one, right?
Yes, one followed by 2 digits, plus 2 digits.
Yes, yes.
Okay. And obviously from the next class onwards, I will not give a very detailed presentation, but I want you to do the project and show it to me. Okay. I will be giving you the manual by tomorrow, or by tomorrow. Okay.
Sir, can you please send the list of the experiments?
Oh, I forgot.
Yes, sir.
Yes, I will be sending you just now.
Okay, sir.
Okay. Sudhakar sir, I have completed my demonstration. If you want to add on some points, you can add, or we can end the session. Okay. Madam, you have taken the attendance.
हाँ सर, स्क्रीनशॉट ले गया है. अभी भी रोल कॉल कर दूंगी.
A roll call as you wish. आप कर लीजिए.
हाँ.
Absent roll numbers बाद में देख लीजिए, कर लीजिए.
Okay, respond your roll calls. 398. 99, 401,
TC1.
Madam, I think this is a different
sorry.
section.
Four, it is one, huh? Roll 1,
Present, ma'am.
2,
Present, ma'am.
4,
Present, ma'am.
5,
Present, ma'am.
7,
Present, ma'am.
10,
Present, ma'am.
12,
Present, ma'am.
13,
Present, ma'am.
14,
Yes, ma'am.
15,
Present, ma'am.
16, 16, 17,
Present, ma'am.
18,
Present, ma'am.
19,
Present, ma'am.
21,
Present, ma'am.
22,
Present, ma'am.
23,
Present, ma'am.
24,
Yes, ma'am.
26,
Present, ma'am.
27,
Present, ma'am.
28,
Present, ma'am.
30,
Present, ma'am.
31,
Present, ma'am.
32, 32, 33, 33, 34,
Present, ma'am.
36,
Present, ma'am.
37, 38,
Present, ma'am.
39,
Present, ma'am.
40,
Present, ma'am.
41,
Present, ma'am.
42,
Yes, ma'am.
43,
Present, ma'am.
44,
Present, ma'am.
45,
Yes, ma'am.
46,
Present, ma'am.
47,
46. Present, ma'am.
48,
Present, ma'am.
50, 50
Yes, ma'am.
last time absent है 51,
Present, ma'am.
52,
Present, ma'am.
53,
Present, ma'am.
54,
Present, ma'am.
55, 56,
Present, ma'am.
57,
Present, ma'am.
58,